Hi, and welcome back to Elementary Algebra. I'm your instructor, Amy Fuchssteiner, and we are going to be looking at section 6.4 today. 6.4 is still in trinomials. We are going to work on the ability to recognize the patterning of perfect square trinomials. You may recall that we did talk about this in an earlier section. When we were multiplying trinomials, that if you have a binomial that is being squared, so the sum of two terms here is called a binomial, and we are squaring it, that this is the same as a plus b times a plus b, and that will give us a squared plus AB for the outside terms, plus another AB for the inside terms, plus a B squared. Or A squared plus 2ABs plus B squared. I have referred to this as square plus the multiplied double plus a square. So square, multiply, and double, and then square again. And that gives you the trinomial, a squared plus 2ab plus b squared. Similarly, if you have a binomial difference that's being squared, that this is a minus b times a minus b again, or a squared minus ab for the outside minus ab, whoops, for the inside, plus b squared, or a squared minus 2abs plus b squared. Again, a square, multiply the two parts of the binomial together and double it, giving us a minus 2ab, and then plus the second term in the binomial squared again. So again, I have square, multiply, double, square. Only because it's subtraction, this time we're subtracting it. So we got square minus multiply, double, plus a square. Okay? What we want to practice in this section is we're going to, together, practice this recognition of perfect squares and the recognition of these particular patterns. We're going to be looking at the trinomials and determining back what the factored square would be. Okay? So we're going to be looking at the trinomials and working back to the squared factors. Now, in order to do this, it helps to be very familiar with integers and their perfect squares. So here in this block, we have the numbers 1 through 24 and all of their squares. I think most of you are familiar with very many of them. You may not be familiar with all of them. Part of the reason it helps to be familiar is because you can more readily recognize when this pattern is in play if you know things like 289 is 17 squared. Because then you're not trying to figure out how to get to a 289. You know it's 17 squared, right? 17 is probably not one of the ones that you will need to be most familiar with. I would say most numbers under 10, so the 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 are all very good to be familiar with. In most cases, you may know them up to 12. You may know 121 and 144 as well. Studied math. I had to know them up to 25, right? At some point, it became very useful to know them all the way up to 25. This is up to 24. But I thought I would give you one place where you could take a picture or screenshot, or if you've got the notes printed out, where you could highlight that in your notes so that you could reference that if needed. Okay? All right. So we are going to determine, we're only going to determine yes or no, are these perfect square trinomials? So the problems on this particular front page, all we're going to do is determine if it is a perfect square trinomial or not. If it is not, then we want to know what is messing it up. Like why, what What is it about that trinomial that makes it not a perfect square trinomial? Okay? All right, remember again, the idea here is, do you recognize the pattern where the first term is a perfect square, the second term is a multiply double, and the third term is also a perfect square? Right? So here's how I would do this. May not be how you recognize it, but it is how I. All right, so I'm going to look at x squared. X squared is indeed x times x. That works. That is a perfect square. When I look at 25, I do see that 25 is 5 squared, or I know that it is 5 times 5. If this is a perfect square, then this middle term should be 5x doubled, or 10x. So I've got a perfect square on each end, and the middle term is the square roots, the 5 and the x, doubled. So yes, this is a perfect square trinomial. I've got a square, they're multiplied together and doubled, and I've got a square again. Right? Let's try number 2. Number 2, q squared is q times q. 9 is 3 times 3. If I multiply 3 times q, I should put a tail on those guys, and I double it, whoops, not square it, times 2, that would be 6q, and this is 9. Okay, so this one is not a perfect square trinomial. There's actually 2 giveaways here. First of all, I should have, since the square root of 9 is 3, I should have 6q in the middle, double 3, or 6 in the middle. So that's the first reason why. But the second reason is this. If you look at the pattern, do you see how that's a minus 9? In our patterning, it's always a plus square. It's always a plus square. This is a minus square. So this is not going to be a perfect square trinomial. Notice I'm not telling you whether or not it's factorable. We haven't even determined whether or not it's factorable. We're just looking at whether or not it's a perfect square. Can I apply this pattern to this trinomial? And the answer is no for this one. Okay, let's look at problem number 3. Is this a perfect square trinomial? Well, h squared is indeed h times h. But 8, we go from 4 to 9. 8 is not a perfect square. And if that is not a square, then my answer here is no. This is not, I cannot apply the square trinomial pattern. If we look at number 4, this is m times m. This is 3 times 3. 6 is 3 times 2 times m. That works, right? Or 2 times 3m. I like that better. 2 times 3m. That does work. So this is square multiply double square. But again, the same as before. That should be a plus 9. And it's a minus 9. So this is again a no. Good? Okay. So let's look at x squared minus 14x plus 49. X squared is indeed x times x. 49 is indeed 7 times 7. If I take a 7 and an x and I multiply them together and I double it, do I get a 14x? Well, this is a minus. So I would need to take a minus 7. Can I do a negative and negative? Yeah, I can. Negative times negative is still a positive. So yeah, this one will be. For sure. That one definitely works. All right, what about number 6? Oh, number 6 is a bit tricky. Okay, so in number 6, is 6x squared a perfect square? I mean, I can do 36. That is indeed 6 times 6. But this 6x squared means that's not factorable. That's not perfect. Or not a perfect square. So since the first term is not a perfect square, this is a no. Oh, but do you see what I see? Right? Like I could factor a 6 out of this. If I factor a 6 out of this, Then I have x squared plus 4x plus 6. Now the x squared is perfect, but the 6 is not. Okay, so yeah, so again, we're running into that problem where the beginning and the end need to be perfect squares, and they're not here. So this is not going to be a perfect square trinomial. All right, what about number 7? Well, number 7 is going to run up against the same thing as before, is that's a negative. And according to our pattern, it needs to be a plus b squared and a plus b squared. The middle term can be negative or positive, but that's going to be a plus. So this is again a no. All right, let's try the last one. Is the last one a perfect square? Well, this is y squared is indeed y times y. 225. There we go. It is 15 times 15. So if I multiply a 15 and a y together, and I double it, do I get 30? I do get a 30, but this is a negative 30. So that means I would need both of these guys to be negative 15s, because negative times a negative is still a positive. So that would work. So this is a yes. This is. Okay. We haven't even talked about how to put those factors back in, but I just wanted you to see a little bit of practice about determining whether or not it is a perfect square trinomial. All right, so how do we use that to factor? So our goal here for the second part of this is to look at the patterning to actually factor the perfect square trinomial. So here's what I need you to recognize, that this a squared is indeed a times a, that b squared is b times b. Since the middle term is an a times b squared, the factor here is whatever a is plus whatever the b is squared. So if you can determine what is being squared in the first term and what is being squared in the second term, and you can verify that the middle term is twice the product of those squared, then what you have is whatever a is plus whatever b is squared. It's very similar for the subtraction. A squared is a times a, b squared is b times b, but we want to use the negatives. I know I want to use the negatives because my middle term is that ab multiplied together times a negative 2. Then what I have is whatever that a value is minus whatever that b value is squared. Using subtraction here is going to get us subtraction as the middle term. So this middle term is what's determining whether I use a minus b quantity squared or a plus b quantity squared. Let me show you how it goes, okay? So for number 9, I have x squared plus 18x plus 81. So x squared is indeed x times x. 81 is indeed 9 times 9. Now I will check, and I will take an x and a 9 and multiply it together. And then I will double that, or 2 times 9x, which is indeed 18x. This tells me that the x and the 9 are what go in my binomial. And since it's plus, I'm going to use the plus. So this will be x plus 9. Technically times another x plus 9, which is x plus 9 squared. Right? That's what the squared means. It's twice. So I use an x plus a 9 from the first and an x plus a 9 from the second, x plus 9, or x plus 9 squared. Lots of people forget that middle term there, or the middle step here. It's fine. We can go from here to here. That's the whole part of this, is that we want you to be able to practice enough to make those kinds of jumps to the actual factored form. All right, taking a look at number 10. X squared is indeed x times x. 64 is indeed 8 times 8. So this should be x and 8 with another x and 8. Now, the question is, if I take the 8 and x and I double it, do I get the 16? I do, but I have to use a negative. And since I have to use a negative, this will be x minus 8, or x minus 8 squared. Okay, what if there's a coefficient? No big deal, we got this. With number 11, we have a 9r squared. The first thing I want to do when I see a leading coefficient is check for a common factor. Is there a number that goes into 9, 24, and 16? There is not. So, since there is not a common factor, I'm then going to check. R squared is r times r, but 9 is also 3 times 3. So this could be 3r times 3r. 16 is also a perfect square, 4 times 4. If I multiply each of those roots together, so 3r times 4, and then I double it, do I get 24r? And I do. 3 times 4 is 12, times 2 is 24. What that tells me is that this can be factored into 3r plus 4 times 3r plus 4, or 3r plus 4 squared. This is indeed a square, multiply double, square. Trying number 12. For number 12, I have a 4g squared plus 20gh plus 25h squared. There is nothing that can be pulled out of a 4, a 20, and a 5. Not the same thing anyway. G squareds and h squareds, nothing. There's no common factor here. So since there's not a common factor, I'm going to look for roots. 4g squared can break into 2g times 2g. That is a perfect square root. The 25h squared can break into 5h times 5h, or something times itself. If I multiply one pair together, so if I do 2g times 5h and I double it, do I get 20gh? 2, 4, 20, yes I do. That tells me that this will factor into 2g plus 5h times 2g plus 5h, or 2g plus 5h squared. Notice, right, that all of these with a plus, 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 all ended up with a plus, plus, plus. And the one with a minus ended up with a minus. So the sign on the middle term, if you're doing a perfect square, will tell you what sign belongs in your factored binomial. Okay? All right. What's next? Oh, all right. These guys have a GCF. These guys have a common factor. All right. And then if it's prime, we'll say so. Okay. So we could end up with some primes here. Let's try. Oh, this is weird. We're good. Okay. So I've got a 25x to the third plus 10x squared plus x. I can pull an x out of all of those. And then I will have a 25x squared plus 10x plus 1. All right. As always, when I have a greatest common factor, I like to draw a line just to sort of keep it visually separated for me. 25x squared, I'm going to pull my orange here, would be 5x times 5x. Is 1 a perfect square? I can get, this one can be tricky. 1 is indeed 1 times 1. So 1 is a perfect square, although we don't often think of it like that. It is. 1 is a perfect square. So I've got a perfect square to begin. I've got a perfect square to end. And then if I multiply one from each, 5x times 1, and I double it, do I get the middle term? Yes, indeed I do. That tells me that this will factor into 5x plus 1 times another 5x plus 1, which I can simplify as 5x plus 1 squared. I'm going to bring that x down. So completely factored, I have x times 5x plus 1 squared. Okay, what about number 14? Oh, Lord, that's messy. Okay, so I have 24s squared t squared minus 18s squared t cubed minus 8s squared t. I think I can pull out an s squared t, and I can also pull out can't pull out an 8. What about a 4? 4 didn't go into 18. I can pull out a 2. They're all even. I can definitely pull out a 2. So I'm going to pull out a 2 s squared t. That's going to leave me with a 12t minus 9t squared minus 4 minus 4. Okay. All right. Now, oh no. Okay. So now I do that. This trinomial is not in order, so I'm going to reorder it. Minus 9t squared plus 12t minus 4. Oh boy. Okay. Do you see how it's leading with the negative? I don't like that. So now I'm going to pull out a negative 1. So I'm going to pull a negative 1 out. And that's going to give me 9t squared minus 12t plus 4. Okay. So now I'm going to take that negative 1 times all of this for negative 2s squared t times 9t squared minus 12t plus 4. Okay. So I basically didn't catch the negative because I should have ordered first. If I would have ordered first, I wouldn't need that extra step. So if I would have put, because this is degree 2, 3, this is degree 5, it should have come first. So if I would have ordered that, I would have done better here. But that's okay. Sometimes if you mess up along the way, you just need to know how to get back on track, right? Okay. So now that I've got that greatest common factor out, now let's see. 9t squared is a perfect square. That can be 3t times 3t. 4 is indeed 2 times 2, also a perfect square. If I take one from each, 3t times 2, and I double it, do I get the middle term? That's 6t times 2, that's 12t, but I would need to go negative here. So this would factor into 3t minus 2, 3t minus 2. And I've got to bring down the negative 2s squared t. So to write this efficiently, I am out of room. That would be a negative 2s squared t, 3t minus 2 squared. There we go. Sorry, I ran out of room. But we're pretty close. All right. Very nice. Okay. Third goal. Second goal? Third goal. Difference of 2 squares. Yeah, we're going to factor the difference of 2 squares. Okay. This one is slightly different. It's the same, but it's different. Okay. Do you see how we have something squared minus something squared? Remember, difference is subtraction. This is the difference of 2 squares. That means we have square number 1, and we have square number 2, and we are subtracting. Okay, so we got square number 1, we got square number 2, and we are subtracting them. This is different than the square of a difference. So the difference of 2 squares is a squared minus b squared. Right? So we've got 1 squared, 2 squared, difference is subtraction, versus the square of a difference, which is a minus b squared. These are 2 different things. So in the first one, we have 2 squares and we're subtracting them. And in the second one, we have a subtraction problem, which we're then squaring the answer to. Okay? There is a very big difference here. They are two different types of problems. So you need to watch out. I know that they look very much the same for you. I know that you're not used to practicing on them. So make sure you practice them. The difference of squares as compared to the square of a difference. They are not the same thing. All right. So we are going to work at the difference of squares. How do I know the difference of squares? Well, again, you've got, it opens with a square and it closes with a square. But there are only two terms and they are subtracted. Right? The difference, the square of a difference. So if you take a difference and square it, this also opens with a square. It also closes with a square. But there will be three terms. Okay? The middle term will be negative, but the ending term has to be positive. So when you do the difference, the square of a difference, you end up with positive, negative, positive, right? So this one is positive, negative. So our first term is positive, but we're subtracting the end term. And for the difference squared, our first term is positive, middle term is negative, last term is positive because we have three terms. The biggest tell-all is that one has two terms and one has three terms. Okay? So the difference of two perfect squares, what you end up with is an a plus b, a minus b. Since there is no middle term, it needs to cancel. So we end up with an a squared plus ab's minus ab's minus b squared. The different signs here cancel out that middle term. They will be opposites. And in order to make those middle terms opposites, when you factor them, one needs to be positive and one needs to be negative. Let me show you the long way round, okay? The long way round is to say that this is a squared plus 0a's minus 16. So if we do our first times our last, we need the factors of a negative 16. That will add to be 0. 16 is 1 and 16, negative, positive, or a 2 and 8, or a 4 and 4. The pair that adds to 0 is a minus 4 plus 4. So I'm going to break that 0 into a squared minus 4a plus 4a minus 16. Does this seem familiar to you? I'm using the previous process, right? So now when I factor by grouping and I look at the first two, I can pull an a out and I'm left with a minus 4. And when I look at the second two, I can pull a positive 4 out and I'm still left with a minus 4. This a minus 4 is in both terms. So I'm going to pull it out front. And I'm left with an a in the first one and a plus 4 in the second one. So I have a minus 4, a plus 4. Notice that the a comes from the a squared, right? A times a. The 16 breaks into a 4 times 4. And if one is positive and one is negative, then I have a plus 4a minus 4a. They cancel each other out and I end up with that 0. So when I simplify it, I just have a squared minus 16. Okay? So the pattern for a squared minus b squared ends up being an a plus b and an a minus b. The difference in signs here is what eliminates that middle term. So to use the pattern, X squared here is x times x. 225 is 15 times 15. In order to make it a negative 225, one needs to be negative and one needs to be positive. That means I factor this as x plus 15, x minus 15. If I want to do the long way around, I come back to these steps with the factoring by grouping, and it will work. So if you don't recognize any one of these, a perfect square, either because it's a sum or difference, or the difference of two squares, newsflash is that, that factoring by grouping process works all the time. Okay. So for number 17, I have an m squared minus 1. M is a perfect square. It is indeed m times m. 1 is a perfect square, but in order to make it negative, I need a minus 1 and a plus 1. That means in factored form, this is m plus 1, m minus 1. Okay. If I have number 19, 4x squared is indeed 2x times 2x. Oh, it's only two terms. When it's only two terms, I know that it is possible to use the difference like this. I know it's possible to use this pattern. That's my cue or my key to looking to see if this pattern will fit. All right, so because it's only two terms, I will then check the difference of two squares. So the difference of two squares tells me if I can take the square root of 4 and the square root of x squared, so 2 and x, and I can take the square root of 49, that's 7 times 7. Okay, since it's only two terms, I need it to be negative here. One will need to be negative and one will need to be positive. So I will do 2x minus 7, 2x plus 7. And then I do it mentally, right? I check in my head. There's a positive 14x, there's a minus 14x, and yep, it would eliminate. So I have a 4x squared minus 49. Okay. Similarly for number 20, I only have two terms. Are they both squared? Yes, a squared and b squared. Are their coefficients squared? 16 is a perfect square, 121 is a perfect square. So this would be 4a and 4a, and this would be 11b and 11b, right? So since there are only two terms, one of these needs to be negative, one of these needs to be positive, I would have 4a minus 11b and 4a plus 11b. Nice. Difference. Okay. What about number 18? Yes, I only have two terms. X is x times x. 9 is also a perfect square at 3 times 3. Now, the problem is this needs to be subtraction. If this is not subtraction, you cannot use something called the difference, because difference means subtraction, of two terms. We cannot use the difference of two terms pattern because I do not have a difference here. I have a sum. So this one, this is not a difference of squares. Whoops. So in fact, this cannot be factored and is prime. When you have just two terms and that plus sign there, that does tell you that you have prime. Squares with a sum. Sum of squares is prime. Okay. Similarly, if we look at number 21, yes, I could pull a 4 out, and then I'd have x squared plus 100. Right? So I could pull 4 out. That x squared is a perfect square. 100 is a perfect square. So that works. 10 times 10, x times x. But this also is not a difference. It needs to be a difference. So while it is not prime, this is as much as I can do to factor it out. I can't go any further than that. That x squared plus 100 cannot break down any further. As much as it pains me and as much as I want it to, it won't work. Okay. Problem number 22. Oh, it's a little bit messy, but let's see what we can pull out of number 22. I can pull out an 8. This has an m squared, that has an m, so I can pull out an m. This has an n cubed, that has an n to the 4th, so I can pull out an n cubed. And then I'm left with m minus 3. I'm taking the m out n. Okay, so I'm able to pull out an 8mn cubed, but I don't have an, these aren't squared. These aren't squared, so I can't use that difference of 2 squareds. I was able to factor out the 8mn cubed, but I couldn't pull anything else out. So this is it. I am done. That's as far as I can go. All right? Not even a difference of squares. Okay. But it serves as a good example of when you cannot. Right? Okay. Oh, a couple of application problems. All right. The maritime signal flag for the letter R is shown. Find the polynomial that represents the area of the yellow region. Express that polynomial in factored form. How would I do just the yellow region? Okay, I'll tell you what I would do. I'm going to break that yellow region into some parts here. Okay. Okay, so that yellow region is going to be 4 of these rectangles, right? Because I've got one there, I've got one here, I've got one here, and I've got one here. So 4 of those. I've got 4 of those yellow rectangles. And then I've got this middle section. So that's how I'm going to build it. I'm going to build this polynomial by finding the area of one yellow section and then multiplying it by 4. And then I'm going to add to that the one sort of black square in the center. Okay, I'm not saying this is going to be the perfect way to do it because I haven't practiced first for the most efficient method. All right. I just saw another way, but let's do this way first. Okay, so if we do the 4 rectangles, so this rectangle is going to be 7 there, and I just need to find this. I need to find that, right? So the long side is 7. Okay. How do I find just that little piece? I know the whole side is x. I know that's 7 and that's 7. Oh, so this is going to be all of x, but without the 7 on each side. So that's going to be x minus 14. Yeah. So this side is 7. That part is going to be all of x minus 7 from the left minus 7 from the right. I did my left and right wrong. So it's going to be all of that x side minus 7 here minus 7 there. Right? So x minus 14. Okay, that's good. Not hard. What about the center? Well, that's this x minus 14 and the x minus 14. Length and width would be the same because that's a square in the center. Okay, so expressing this polynomial. All right, so area is going to equal 4 of the yellows, which is 7 times x minus 14, plus an x minus 14 squared. Oh, okay. All right, so what am I going to get? I'm going to have 4 times 7x minus, yikes, 7 times 14 is 98 plus x minus 14 squared is going to be x squared multiplied double 28x square plus 196. So simplifying, this is going to be 28x minus 98 times 4 is 392 plus x squared minus 28x plus 196. Oh, okay. Well, there's a couple of things in my favor, right? That positive and negative will cancel out. That's good. And I'm left with x squared. I've got a minus 392 plus 198. Whoops, I got to do plus. Here we go. Minus 194. I don't think, let's make sure 14 squared is right. Yep. So then I do 7 times 14 is 98 times a negative 4 is negative 392. Oh, is it 96 again? I think I added wrong. I think I plus 196. Yeah, is a negative 196. Okay, that's good. Whew. This is now that's a difference. That's an x times x. See how it's two terms? I've got to factor it. So now I've got 196, which is indeed 14 times 14. We just did that one. So this would be an x minus 14, x plus 14. All right, and this would be the area simplified and in factored form. Whew. Okay, could I have done that in an easier fashion? Maybe. I mean, I did see something that I could have done. But I think no matter how you did this, you're going to have to build it up and then simplify it a little bit. So, yeah. Okay. All right, one application done. That was a rough one. All right, when asked to factor x squared minus 25, student number 1 wrote x plus 5, x minus 5. And student number 2 wrote x minus 25 squared. Who's wrong? And what happened? Yeah. Yeah, who's right? They're right. This is correct. This guy is wrong. What did they do? What do you think they did? I know what I think they did. I think they just took that squared and put it on the outside because they thought that's how I get a squared. Right? They didn't recognize the pattern for what it was. But what did they do wrong? I can't fully answer that for you because you are meant to explain that. All right. Okay. If you need any help with any of this recognition, please reach out to myself and or to the Math Center, and we would be happy to help you. If you have any questions or concerns, you can email me at fuchssteinera@westerntc.edu, or you can call my Google voicemail as well. You have that information in the Blackboard course. All right. Thank you all. Have a good day. We'll see you next time.